in the previous session, I promised you I would do a bit of homework and actually go through each chapter of the text and find how many theorems there were per chapter. Well, I did that last night, and sometimes he would use the word claim and then give a proof, so I included claims in the number of theorems, and of course corollaries also, kind of theorem. And so I can give you the numbers. I was not surprised. In fact, my earlier, previous day guesstimate, it's a midway between a guess and an estimate, that it would probably be over 100, and probably between 100 and 200. Well, the actual number for all chapters, it's 11 chapters, 10 numbered chapters, and the preliminary chapter 0. There are 147 theorems, inverted commas theorems, so roughly 150. And I'll just give you the breakdowns. So chapter 0 there were 5, chapter 1 there were 11 theorems, chapter 2 8, chapter 3 6, chapter 4 13, chapter 5 14. Okay, now there's a big jump, because now you get into chapter 6 and chapter 10, remember, are the advanced topics. So they're the more the M1, first year master's level. So chapter 6 had 20, okay? And chapter 7 had 22. Chapter 8 had 9. Chapter 9 had 14. And chapter 10 had 25. Right? So that was the final chapter on advanced topics in complexity theory. Complexity means how hard is it, how much effort, like how many computer cycles, computer steps do you need to calculate something. And there are various categories of hardness or difficulty. So hardness theory, or if you like complexity theory, is a hot topic of research, ongoing. Anyway, so 25 theorems in there. So nearly 150 in total. Okay, so we're just in the middle of our first major one. Now the other thing is, you may have noticed, previous session, it sort of cut off rather abruptly. I didn't sort of finish off. I have a 32 giga memory chip that I bought, which is the biggest, the highest capacity that this model of camcorder can take. So I should have plenty of time, but for some reason that I haven't figured out yet, haven't bothered, I only get 7 gigabytes. Now 7 is usually enough for 4 sessions, so most of the time I don't have a problem. But I seem to be overrunning more frequently lately, so what I've done is the last half square, I guess, of the previous session, I've just repeated. I've just written it down again here. So you may be wondering why I didn't talk about it. I just ran out of time. I ran out of memory. So I suppose I should learn. There's a lot of ads on the camera, garbagey ads. I'd just like to remove, but I've got to figure out how to do that, so that I can actually access my full 32G instead of 7, which is sort of ridiculous. So I'm eliminating more or less 7G every day, and so the same, I guess, the same parts of the RAM, the memory, is getting overwritten each day, which is probably, I should spread it out more. I just need to bother to do it. I don't like systems work. It's just my personality. I am not an engineer. Right? I'm more a theorist, not an engineer. Don't have that mindset. Alright, so there's 2 remarks out of the way. So just continuing on, we're doing a proof, remember? We're trying to show that if you have 2 regular languages, so A1 and A2, regular means that each of those languages has a finite automaton, or I just say automaton, that recognizes that language. So you'll have an automaton M1 that recognizes language A1, and you'll have an automaton M2 that recognizes language A2. Okay? And we're in the process now of using a construction proof to build, construct a machine M that simulates the two machines M1 and M2, trying to show that this machine M recognizes the union of those two languages, A1 and A2. So by finding this machine M, if we can do that, then we've found a machine M that recognizes the union, A1 union A2. And if that's the case, therefore, that union, A1 union A2, has a finite automaton, M, that recognizes it. And therefore, by definition, that A1 union A2 is a regular language. Okay? So that means that for like any two languages, regular languages, so for the class or the set, if you like, of all regular languages, if you apply the operator, the operation, union, on any two of those from that class or set, the result is also a regular language. So A1 union A2 is a regular language, and therefore belongs to that set or class of regular languages. And therefore, that class of regular languages is said to be closed under the operation of union. Okay? Remember closure in general? If you generalize the concept, you have some set, call it S, you have some operator, you have some operation, call it P. So if you apply P to one or more members of your set, S, the result that you get, if that result is also a member of your set S, then that set is said to be closed under that operation, P. Okay? That's the sort of general case. The notion of closure, quite important in theory of computation. So we're in the process now of trying to show that regular languages, the set of them, the class of them, the family of them, that class is closed under the operation of union. Okay? And later we'll show that it's closed under the operation of concatenation. And we will show later it's closed under the operation of star. Okay? And these operations are called, generically, regular operations. We're talking about like three regular operators, like the union, that's one operator, a little circle, that was the concatenation operator, and the unary operator, like star, A star, language A, starred, A star, that operator star, to star a language, also closed under that operator, that operation. Okay, so in the middle now of trying to prove that the class of regular languages is closed under the operation of union. Okay, now we're sort of halfway through, more or less, in the proof idea, sort of giving the overview of the proof, and then later we'll give the proof itself. And some of the things that might not be too clear in this current overview, the proof idea, should clarify more when you get to the actual details, the proper proof. Well, that was my experience anyway. Alright, so we're reasoning, if you remember, previous session or so, that our machine M, that's to recognize the union of A1 and A2, it was effectively simulating the two machines M1 and M2. The machine M1 recognizes language A1. Machine M2 recognizes language A2. So we were designing a machine M that would simulate these two machines. And so if any one of those two accepted, either accept A1 or accepted A2, because we're talking about the union, right? So if that happened, then machine M would also accept. That was the sort of core idea. Another major idea was when we're talking about, this is a proof by construction. We have to construct or design machine M. So we don't know the size of the inputs or anything like that. So we cannot draw a state diagram, a state transition diagram. So we have to resort to the other possibility, and that is drawing. Well, not drawing. We will specify a formal. We will write out a formal definition. In other words, the 5-tuple. Okay, we don't have any choice. So when we come to the actual proof, the detailed proof, we will write out that formal definition for M. But at the moment, we're sort of the overview. We're trying to essentially get the basic ideas because they're the heart of the proof. So one core idea is simulate the two machines M1 and M2, and then we start talking about, well, what states, what would big Q be for this M? What would your set of states be? And the idea that we had, like the main idea pretty much for this proof is talk about a pair of states where the first member of the pair is the current state of machine M1, and the second member of this pair is the current state of machine M2. Okay, and that pair, state of M1, comma, state of M2, that pair becomes a state, the current state, if you like, of machine M. Okay, now that's a core idea, that's a basic idea. And then when we come to